So you're often going to find that anytime we're using formulas that involve moles, okay, like the molarity formula, we're going to end up using that formula and also doing stoichiometry. So if you see moles in it, just expect stoichiometry to pop up. All right, so let's do some stoichiometry using the molarity equation. And we're going to begin with example 9.4, which I've got the formula listed out here. A chemist is doing the following double displacement reaction. And it says if the chemist starts with an excess of MgCl2, magnesium chloride, and 150 milliliters of a 2 molar solution of silver nitrate. So that's the AgNO3. So it tells us with that we have 150 milliliters of this, and that we have a 2 molar solution. All right. And so the question is, whoops, what was that? I don't know what that did. There we go. The question then is, how many grams of AgCl should precipitate out of the solution? So we notice with AgCl that it's a solid. So that's a precipitate that occurs in this reaction. And they want to know specifically how many grams of this substance will the equation make. All right, so let's think about what we need to do. Before, in previous chapters, whenever we wanted to find the grams of some substance that was in the chemical equation, they would give us the grams or the moles of one of the other substances in the chemical equation. Well, this time they didn't do that. Instead, they gave us the concentration, which is this molarity value here, and the volume of this AgNO3 solution. Now we remember that the molarity equation is M equals moles over the volume, which is in liters, right? And so what this means is that we can rearrange this equation and say that moles is equal to molarity times L, and we can use those values to calculate the number of moles of AgNO3 we have. And then we're just doing a stoichiometry problem just like we've done before. We'll have moles of AgNO3. We can use stoichiometry to figure out the grams of AgCl, right? So let's plug in the values into this equation here. Now, molarity we can just plug in directly like it is, 2.0. Remember, molarity is moles per liter. And but this second value needs to be in liters. It's currently listed as 150 milliliters. Well, that's the same as 0.15 liters. We just move the decimal place 3 places to the left. And when we do the math with that, we get a value of 0.3 moles. All right. I don't know why I drew that point way out over there. Let me fix that. 0.3 moles. There we go. All right, so we've got 0.3 moles of AgNO3. Now remember, when we were learning stoichiometry, we said this is the path you have to take. You can start with the grams of substance A, and from there go to moles of substance A, and then you can convert from there to moles of substance B, and finally we can go to grams of substance B. So we're ultimately trying to, our substance B is this AgCl, right? But our substance A in this case is the AgNO3 that we just found the number of moles of. So we don't have to worry about grams because we're not starting there. We're starting at our path here, but we need to do this part of the path to figure out the grams of AgCl. All right. So we take 0.3 moles of AgNO3, and we can tell from our balanced chemical equation that 2 moles of AgNO3, we'll put that on the bottom because that's the unit we want to cancel out. 2 moles of AgNO3 is equal to 2 moles of AgCl, because that's what we're trying to convert to, right? 2 moles of AgCl. And then finally, so that's going to, moles of AgNO3 are going to cancel out. We're going to be left with moles of AgCl. Finally, we're going to use the molar mass of AgCl, and we go to the periodic table to do that. And if we go through those steps, we'll see that that 1 mole of AgCl has a mass of 143.32 grams. All right. And so moles of AgCl are going to cancel out right here, and we will end up with this unit of grams of AgCl, which is what we want. So plugging all of that in our calculator, We'll round based on significant figures to get 43 grams of AgCl. And that will be our final answer. So again, the only reason we used our molarity equation, right, was to calculate the number of moles. But at the point we found the number of moles, now we're just doing stoichiometry just like we've done before. Okay, so this is a common scenario, right? We're going to have other equations in the future that include moles in it, and you're going to see we're going to use that equation to calculate moles, and then we're back to doing something like we did here to figure out the grams or the moles of some other substance. All right, let's do one. I know this is new, and I think the more problems you do, the better you'll be. So let's go ahead and do example 9.5 as well, just to make sure that you understand that. Example 9.5 says that a chemist wants to make 300 grams of calcium hydroxide using this reaction. So we're told that CaCl2 in aqueous form plus 2 sodium hydroxide in aqueous form is going to produce calcium hydroxide, CaOH2, which is a solid, and that's going to be added to NaCl. Okay? And we're told we have 300 grams of calcium hydroxide. Now, calcium hydroxide, you have to be able to identify that in the chemical equation, right? The one that begins with calcium and has the hydroxide polyatomic ion in it is this first product that is a solid. And so we're going to put 300 grams over that. And what they want to find is, they said that we have a 3 molar solution of NaOH, right? 3 molar solution of that. They have 2 zeros, yeah, 3.00 molar solution of NaOH, sodium hydroxide. And they want to know what volume of that solution will we need to use. Okay, that's interesting. We want to know what volume of this solution we'll need if the goal is to produce 300 grams of CaOH. How do we go about figuring that out? Well, to determine the volume of this, given the molarity of this, what are we going to need to find? Again, if you think about the molarity equation, molarity equals the number of moles over the volume in liters. So if I'm trying to find the volume in liters and I've got the molarity, I need to know the number of moles, right? So how could we figure out the moles of NaOH given the information that they've given us? Well, this one we're going to start with stoichiometry, right? So again, our stoichiometry path says that we can go from grams of substance A. This time our substance A is going to be our CaOH. So I'm actually going to write that down. Grams of CaOH2. All right. We can go from grams of that to moles of that, moles of substance A, CaOH2. And then once we get the moles of that, we can go to moles of substance B. In this case, substance B is our NaOH, right? Moles of substance B, NaOH. And we could, of course, find the grams of NaOH, but we don't need it for this, right? What we're looking for is the moles of NaOH, so we can plug it in this formula here and calculate the volume. So that's the first calculation we need to do. So we've got 300 grams. You know what? Actually, I can just do this. I'm gonna just erase, just to make sure we're understanding how to go, how we're using this path here. I'm just going to keep these units, and I'm going to just put numerical values in front of it. So 300 grams of CaOH, and we're going to multiply that by 1 mole of CaOH is equal to, we go to our periodic table, we say what would the atomic mass be if we have 1 Ca, 2 O's, and 2 H's, and we come up with an atomic mass of 74.10 grams, which is therefore the molar mass of CaOH2. Right, so grams will cancel out. And then if we're going to go from moles of CaOH to moles of NaOH, we're going to use these stoichiometric coefficients in front of these guys, right? There's an understood 1 here. And so we know that 1 mole of CaOH NaOH2 is equal to 2 moles of NaOH. So we do the math with that, plugging all of that in our calculator. We finally get a value of, let's see, where is that calculation? 8.089. 8.08. No, sorry, 0.98 moles of NaOH. All right, so that's what we need now to plug in our formula right here. Now, we're solving this formula for volume because we're trying to find the volume of it, right? So we're going to rearrange this equation and solve for this L right here, right? That's our volume unit. And if we rearrange it, a couple of ways you can think about it. Most students seem to do best with this if they think about it as cross multiplication. So using cross multiplication, we get that M times L equals 1 times mole, or moles, right? And then if we're trying to find the number of liters, we're going to divide both sides by M, right? That'll cancel out these M's here. So the equation that we're actually using is that the number of liters is equal to the moles of the substance divided by the molarity. Divided by the molarity of the substance. So we found the number of moles to be 8.098 moles of NaOH. And our NaOH has a molarity of 3.00 molarity. They gave us that in the problem. And so doing the math with that, we get 2.70 liters as the volume. That's the volume of NaOH we would need in this balanced chemical equation to produce 300 grams of CaOH2. Now again, like I've told you guys since the beginning of the class, what are we doing? We're doing a bunch of unit conversions, right? These unit conversion things are not going away. We're going to keep running into that over and over again. So figure out what you need. In this case, we need to define the moles of this stuff here. And you just do your unit conversions to go from grams of this to moles of this. And then you can plug that into this formula, right? After we've rearranged it this way to figure out what the number of liters are that would be needed to make that many grams. All right, so I told you in this chapter we've got more than one concentration unit that we use. And the first one that we learned was molarity. Well, now we're going to learn a second one. And the second one is molality. Sounds pretty similar. And like I said, we're not going to use molality as much as we use molarity the rest of the year. But it is another important concentration unit, so let's make sure that we understand that. And we've got a formula that goes with molality, just like we had a formula that went with molarity. Molality is spelled this way, and we're going to use a lowercase m to represent molality. That's a little confusing, I know, because we also use lowercase m to represent mass. We also use a lowercase m to represent meters whenever we use that unit, but unfortunately, that's the letter we have. So we're going to use a lowercase m for molality as well. And where molarity told us what the relationship was between the moles of the solute and the volume of the solution, molality is going to tell us the relationship between the moles of the solute and the kilograms. I have lost my cursor here, and I'm not sure. It's making it a little hard to see this guy. Let's see if I can get that back somehow. It's not coming back. What if I do this? There we go. Okay, so moles of solute divided by the kilograms of the solvent. All right, so whereas before we were looking at a relationship between the moles of the solute and the volume of the total solution, here we're looking at the relationship between the moles of the solute and the kilograms of the solvent only. All right, so we need to. That's the equation we're going to use as we talk about molality. And let's just do a quick example to see how we might put that equation into action. It says a chemist, this is 9.6, a chemist dissolves 50 grams of AlCl3, 50.0 grams of AlCl3 into 350 grams of water. So 350 grams of H2O, right? And they want to know, what is the molality of the solution? Well, the solution asks us for the moles of the solute. So what is the solute here? It's important that we know which one's the solute. We've got AlCl3 and we've got H2O. The solute is what is dissolved into the other substance, and so that's the AlCl3, right? The AlCl3 is dissolved into the H2O. So we need to find the moles of this guy. Well, how do we go from grams to moles of a substance? We use the periodic table, using the molar mass. And if we go to the periodic table, we see that the molar, I just realized I left off an L right there. We go to the periodic table and look up the molar mass, do the calculation to figure out the molar mass of AlCl3. We'll see that it's 133.33 grams per mole, right? So that allows us to convert from 50 grams of AlCl3, keep wanting to leave that L off, to moles of AlCl3, because we know that 1 mole is equal to 133.33 grams, and that's going to give us a value of 0.375 moles of AlCl3. All right, that's the moles of our solute. That's the top part of our equation that we have here for molality. And the bottom part of the equation requires us to find the kilograms of the solvent. The solvent is H2O, but they did not give us kilograms. They gave us 350 grams. Well, similar to when we had milliliters before and we needed to convert to liters, we moved the decimal place 3 places to the left. We're going to do the same thing now. To go from grams to kilograms, we move the decimal place 3 places to the left. So this is going to be equal to 3.350 kilograms of H2O. And so now we have what we need to plug into our chemical, to our molality equation right here. Moles of solute is 0.375 moles of AlCl3, right? Divided by 0.350 kilograms of H2O. And that's going to give us finally a value of 1.07. Now that unit would be moles per kilogram, right? But just like we did before, where we used a capital M to represent moles per liter because we're finding molarity, here, since you're finding molality, you can just say 1.07 followed by the little m to designate molality. Pretty cool, right? So we're pretty close to being done with this chapter. We've got 2 more concepts that we need to cover, but they're related, and we're going to revisit this molality equation because we're going to have to calculate molality to use these next 2 equations as well. All right, so stay tuned for that last video.